Acids and bases. In this section, we will talk about two definitions for the terms acid and base, the Bronsted-Lowry definition and the Lewis definition. According to Bronsted and Lowry, an acid is any species which is able to donate a proton, and a base is any species which gains a proton. So here is a simple acid-base reaction wherein you can see that the HCl is going to behave as an acid because it has the ability to donate this hydrogen, and the water is going to behave as a base because the oxygen has got two lone pairs of electrons, and one of these lone pairs can be used to grab this hydrogen. So HCl is behaving as an acid and water is behaving as a base. When this reaction happens, there is a new base and a new acid that has been created. So this is the new base that is created, and this is our new acid that is created. And the new acid and the new base can be called as conjugate acid and conjugate bases respectively. So this is our conjugate acid and this is the conjugate base. Or in other words, H3O plus is the conjugate acid of H2O and Cl minus is the conjugate base of HCl. So we can call this as acid-base reaction, or we can also call this as proton transfer reaction, because a proton has been transferred from the acid to the base. So on the whole, an acid is any substance which has the ability to donate an hydrogen, and a base is any substance which has the ability to grab the hydrogen. In general, the acid-base reactions are reversible, which is always shown by the double-headed arrow. So if you take a look into this reaction, A plus B can give C plus D, and C plus D can also form A plus D. But this reaction right here is an irreversible reaction. So once A plus B is converted into C plus D, they will not be able to go back to A and B.
Here is another acid-base reaction. Ammonia reacts with water to give ammonium ion and hydroxide ion. In this case, ammonia is going to act as a base and water is going to act as an acid. Water is amphoteric in nature, so it can behave as both acid and as well as base depending upon the other reactant. Ammonia with its lone pair of electrons on nitrogen is going to go and obstruct one of the hydrogens from water, creating the ammonium ion, which is the conjugate acid of ammonia. And the hydroxide ion is created by losing the hydrogen from water molecule, and therefore this should be the conjugate base.
Let us now look into the definitions for acidity and basicity. What is acidity? Acidity is the tendency of a compound to lose a proton, whereas basicity is just the opposite, where it has affinity to a proton. Now, when you say that an acid is very strong, then it has greater tendency to lose a proton, and therefore the conjugate base should be a weak base, which means it is going to have little affinity towards proton. So on the whole, we can derive a relationship between acid and its conjugate base, wherein we can say stronger the acid, weaker is its conjugate base. And the opposite is also going to be true, which means if there is a weak acid, then the conjugate base that it's going to give us should be a strong conjugate base. Strong base. Right? So weaker acid will always give us a strong conjugate base, whereas a strong acid will give us a weak conjugate base. Acids have different strengths. When you have a strong acid such as hydrogen chloride and you dissolve it in water, what's going to happen here is most of the hydrogen chloride molecules are going to get dissociated, which means it is going to break into ions, right, favoring the formation of the products. But when you take a weak acid such as acetic acid and dissolve it in water, only a very few molecules of acetic acid is going to dissociate in ions. The degree to which an acid dissociates in aqueous solution is given by the equilibrium constant, which is denoted by the symbol K equilibrium. And it is calculated using this formula right here, where the concentration of the products is divided by the concentration of the reactants. This square bracket right here is going to represent the concentration, and it is always going to be in most of the times it's going to be in moles per liter. Now, this is normally done in very dilute solution, which means there is going to be huge amount of water, and therefore it can be taken as a constant. So we can club these two constants together. We can club Ka equilibrium and this constant together and bring it on one side. And now we can call this with a new expression called as Ka, which is the acid dissociation constant. So the acid dissociation constant is basically the equilibrium constant multiplied by the molar concentration of water, which is equivalent to 55.5 moles per liter or molarity. Now, what is the significance of this Ka and how is it going to relate to the acidity? In general, larger the Ka, stronger would be the acid. And the opposite is going to be true, which means if you have a compound which has a smaller Ka, then it is said to be a weak acid. Strength of the acids. Acids can be classified as very strong acids, moderately strong acids, weak acids, very weak acids, and extremely weak acids, depending upon the pKa values. Now, we have talked earlier how Ka can be used in order to determine the strength of the acids, right? But it is more convenient to use the pKa. Scientists always like to use pKa. Now, here is the relationship between pKa and Ka. pKa is equivalent to negative logarithm of Ka, which means
the stronger acid will have a larger Ka but a smaller pKa. The concentration of protons in the solution is given by pH. pH is equivalent to the negative logarithm of H plus ions. You can also replace this with H3O plus because the protons are solvated in water. We should not get confused between the terms pH and pKa. pH is used to refer the acidity of the solution, whereas pKa is used for referring the acidity of the compound. This chart right here gives the pH of some of the solutions that we encounter in our day-to-day life. As you can see from here, lemon juice has a pH of about 2, which means it is going to be strongly acidic compared to the milk that we drink, which has a pKa of about 6.8. And similarly, coffee is more acidic than rain.